Okay, let's unpack this. Have you ever stared at a problem, maybe a math problem, maybe something else entirely, and just felt completely convinced it was too complex,
Hmm.
too intricate to ever yield an exact answer? That feeling of hitting a brick wall where maybe the best you could possibly hope for was just a really, really good guess.
Right, an approximation.
Exactly. Well, today we're diving into something that honestly fundamentally turns that whole notion on its head.
And what's really fascinating here, I think, is that we're not just hunting for those approximations, which, let's face it, are often the best we can hope for in really complex scenarios.
True.
No, instead, we're seeking absolute symbolic exactness. This deep dive is going to illuminate the elegance of a method specifically designed to bypass the traditional limitations of algebra.
Especially when it comes to solving these really high degree polynomials.
Precisely.
That's right. So, our mission today, if you will, is to explore a truly groundbreaking mathematical discovery. It centers around Mourad Sultan Ezouidi and his revolutionary theorem.
He's made quite a bold claim.
He really has. The claim is that exact symbolic solutions, not approximations, can actually be found for polynomials that were traditionally considered. It centers around Mourad Sultan
unsolvable
in that exact way.
Yeah, beyond the reach of standard formulas.
And to put this to the test, we're going to tackle a specific challenge, a really specific one. We're talking about a colossal 18th degree polynomial.
Not exactly your high school quadratic.
Not even close. So prepare for what we hope will be an aha moment as we uncover how this method delivers precision where, frankly, other methods just falter. So let's set the stage properly. Our target for today's deep dive. It really is a monstrous 18th degree polynomial.
Mm-hmm.
I mean, imagine an equation that just stretches across the page, a seemingly endless string of variables and coefficients.
Mm-hmm.
It almost looks like it was designed purely to intimidate.
It certainly has that effect.
It starts, x to the power of 18, okay, then minus 18x to the 17th power, then plus 153x to the 16th. And it just keeps going, term after term after term, all the way down to a constant, the plain number 4 at the end, with the whole thing equaling 0.
It's a mouthful.
It really is. You can see the full daunting equation in our show notes if you want brave looking at it directly. But the key thing is, its sheer intimidating size and complexity. Our sources actually call it a significant challenge.
And it feels like a bit of an understatement, doesn't it?
Absolutely.
It absolutely is. When faced with an equation like that, the immediate inclination for most mathematicians, really for centuries, has been to turn to what we call numerical approximation methods.
Okay, like what?
Well, think of techniques like Newton's method, for instance. That's a common one. And these are powerful tools, there's no doubt about it. They allow us to get very, very close to the true roots, the true solutions of a polynomial.
Right.
You can iterate the process, refine the answer, and get a result with, many, many decimal places of precision.
So, okay, if they can get us very, very close, as you say, why isn't that good enough? I mean, what's the inherent problem with these numerical approximations? Is not close enough sometimes?
That's a really crucial point. While these methods are incredibly powerful, they are fundamentally inherently prone to errors. Each step you take in the approximation process, each calculation, introduces a tiny, tiny bit of imprecision. And the problem is, these small errors can accumulate. They can add up over many iterations.
Okay, so rounding errors and things like that.
Exactly. You're always at risk of rounding errors, and maybe more importantly, you can never guarantee an exact value. You can never be 100% certain. So you might get an answer like, say, 3.14159.265, which looks a lot like pi.
Right.
But you can't be absolutely certain if it's truly pi, the exact irrational number, or just something incredibly close to it. Now, for many practical applications, in engineering or physics, very close is often perfectly acceptable. It does the job. But in pure mathematics, and certainly in fields where absolute precision is paramount, that slight uncertainty, that little bit of doubt, can actually be a significant barrier. It matters whether it is pi or just near pi.
And this isn't just about these sort of practical limitations of calculation, is it? There's a deeper, more fundamental theoretical barrier at play here too, something called Abel's theorem.
Indeed. Abel's theorem, or more accurately, the Abel-Ruffini theorem, has been a cornerstone of algebraic theory since the early 19th century. Niels Henrik Abel provided a crucial proof.
Okay.
And what it essentially states is that for polynomials of degree 5 or higher, so 5th degree, 6th degree, all the way up there is generally no formula that can express their roots using only the basic arithmetic operations.
Addition, subtraction.
Right. Addition, subtraction, multiplication, division, and what we call radicals.
Radicals being like square roots, cube roots.
Exactly. Square roots, cube roots, fourth roots, any kind of nth root.
Mhm.
For polynomials of degree 4 or less, we do have well-known formulas. We all learn the quadratic formula for degree 2, and there are more complicated but still explicit formulas involving radicals for degrees 3 and 4. But Abel's theorem told us, basically, beyond degree 4, don't expect a neat, tidy solution using only these tools, arithmetic and radicals.
Wow. So for almost 2 centuries, this has been a recognized barrier in mathematics. It essentially told mathematicians, okay, for these higher degree equations, you could approximate the solutions maybe very well, but you generally can't get that clean, elegant, exact symbolic solution using radicals.
That's the key part, using radicals.
It feels like being told you can climb near the summit of a mountain by scrambling up loose rocks, but there's no clearly defined, elegant path made of solid steps to get you to the very peak.
That's a pretty good analogy. Abel's theorem didn't say these polynomials had no roots. They absolutely do. The fundamental theorem of algebra guarantees that an nth degree polynomial has exactly n roots, possibly complex and possibly repeated. But Abel stated that you couldn't generally express those roots in that specific algebraic form using only radicals. And this had profound implications naturally for how mathematicians approach these higher degree equations.
How so?
Well, it shifted the focus. If you can't find the exact algebraic solution in radicals, you then focus on developing better and more efficient numerical methods to approximate them. Or you delve deeper into the abstract structure of equations, like Galois theory did, which grew out of these questions.
Right.
Ezouidi's theorem, however, enters this landscape. Well, it enters with a direct contradiction. Maybe not to the letter of Abel's theorem about radicals, but certainly to the spirit of that limitation for finding exact solutions.
How does it contradict it?
It demonstrates that even polynomials that do have radical roots, or perhaps even those previously thought to be beyond any kind of exact symbolic solution, can in fact be solved exactly symbolically, just not necessarily in the traditional radical form that Abel's theorem was addressing.
Ah, okay. So it's not finding roots with simple square roots and cube roots necessarily.
Not necessarily, no. It's about finding them symbolically and exactly through a different, perhaps more complex, but ultimately precise methodology.
Got it. So summing up this first part then, the old ways, the classical algebraic methods focused on radicals, and even our best numerical approximation techniques. They were fundamentally insufficient for finding guaranteed exact symbolic solutions to monsters like our 18th degree giant.
Correct, there was a limitation.
Which means there was a desperate need, really, for a new approach, a potential breakthrough that could deliver that kind of precision, going beyond just approximation. Okay, so this is where it gets really interesting, I think. Instead of just chipping away at approximations, getting closer and closer but never quite there, or being resigned to the limits suggested by Abel's theorem for radical solutions, Ezouidi's theorem comes along and promises to basically hand us the precise symbolic answers on a silver platter.
Well, maybe not a silver platter. There's some serious work involved.
Okay, fair enough. But the promise is exactness. It feels like a completely different mindset for tackling these problems. What is the core promise of this theorem?
The core promise is, pretty revolutionary. Ezouidi's theorem provides a systematic, step-by-step way to break down these seemingly intractable polynomials, even very high-degree ones, and find their exact symbolic values for the roots.
Exact symbolic values.
Exactly. And crucially, it does this in a way that avoids the pitfalls of numerical methods, specifically the accumulation of errors. It's not about getting closer and closer. It's about defining the solution perfectly, symbolically, right from the structure of the polynomial itself.
Okay, so how does it manage to do that? How does it seemingly get around what Abel's theorem suggested was, well, generally impossible for polynomials of such high degrees using radicals? Is it just finding some clever loophole in the math?
I'd say it's more profound than just a loophole. It's really a redefinition of the entire approach. The very essence of this theorem lies in its departure from those established norms. It explicitly excludes all classical methods. It doesn't try to operate within the framework that Abel's theorem showed was limited for radical solutions in higher degrees. It doesn't try to find a clever way to express roots using only radicals for a degree 18 polynomial, because Abel essentially said that wasn't generally possible.
So just sidesteps that whole issue.
It completely bypasses it. Think of it as developing a new mathematical language or perhaps a new set of tools specifically designed for this purpose. It provides a new set of rules, a different algorithm that allows for the derivation of precise, solvable roots for equations that were once deemed out of reach by traditional algebra and numerical methods alike.
So it's not just an improvement on old methods.
No, not at all. It's a fundamental redefinition of what's possible in terms of algebraic solvability for these kinds of equations.
That's quite a claim.
Yeah.
So if it excludes classical methods, how does it actually work then? What's the underlying concept? Is it some kind of transformation?
The central idea, the core mechanism, is what the source describes as a recursive process.
Recursive?
Yeah.
Meaning it loops back on itself somehow.
In a sense, yes. Each step depends on the results of previous steps. Think of it like carefully dismantling a very complex machine piece by piece, layer by layer, to understand its fundamental operations from the inside out.
Okay.
Rather than just, looking at the machine from the outside and guessing how it works based on inputs and outputs, which is kind of what numerical approximation does.
Right, like probing it.
Exactly. With this recursive approach, you don't try to solve the whole massive 18th degree polynomial all in one go. That would be overwhelming. Instead, Ezouidi's method involves deriving the solution step by step.
Yeah.
There are specific, predefined formulas laid out by the theorem. These formulas act to break down the polynomial into more manageable components. Each step in this recursion builds upon the results calculated in the previous step. It systematically works its way towards the exact symbolic values of the roots.
So it's this methodical breakdown, this step-by-step process that allows for the precision.
Precisely.
Yeah.
Because every single calculation performed within this recursive sequence is purely symbolic. It's manipulating symbols based on the initial coefficients. It's not introducing numerical approximations at any stage. No rounding, no estimating.
So it's not really a shortcut then.
Yeah.
Sounds like it could be quite involved, but the key is that it's a very precise step-by-step disassembly that ultimately leads to exactness, not approximation.
That's a very good way to put it. It can be computationally intensive, yes, but the payoff is that guarantee of symbolic exactness.
That's really fascinating. All right, so we've talked about the promise, this idea of exactness, and the concept, this recursive disassembly. Now, let's try to get into the how a bit more without getting completely lost in the weeds of every single symbol, because I imagine the formulas are quite dense.
Mm-hmm.
How does Ezouidi's theorem actually take that monstrous 18th degree polynomial we mentioned and begin to transform it? What's the first step?
Okay, the first crucial step is to express the original polynomial, the by 18, 18 by 17, plus 153 by 16, and so on, in a specific, generalized symbolic form.
It's multiple.
Yes. Instead of using the specific numerical coefficients like nag of 18, 153, etc., we rewrite it using a new set of symbolic coefficients. The source material represents this as by 18 war, Sierra by R17, plus S firm by 16, it's Sierra by 15, and so forth, all the way to the constant term as 17R. These scare R symbols are our new focus.
So these ISCA coefficients, are they directly related to the original numbers like nag 18, 153?
They are derived from the original coefficients, but not in a simple one-to-one way. The key insight here is that Ezouidi's method then focuses on calculating these new symbolic coefficients, these scalar values. And they are derived recursively, step by step, using the coefficients of the original polynomial as the starting point.
Okay, so it's not just relabeling the terms, it's the beginning of a deeper analytical process.
Exactly. It's setting up the framework for the recursion.
And this is where that core recursive formula comes into play, isn't it? The one that looked like maybe a dense string of mathematical symbols when you mentioned it earlier.
Yes, that formula is really the engine driving the entire process. At its heart lies this recursive relationship. The source gives it as SK1R, CKR. Nevis SR, SR1R.
Whoa.
Now, I know just saying that aloud doesn't instantly click for everyone, and we don't need to perform the calculation here, but let's break down its function conceptually. Think of it less as just a static formula and more as an algorithm, a recipe for generating these S coefficients.
A recipe, I like that. Like a mathematical machine where each step feeds into the next.
Precisely. It's building towards that precise solution methodically.
So what are the ingredients in this recipe? Can we break down the parts of that formula a bit?
Sure. The CKR terms, those are binomial coefficients. You might remember them from Pascal's triangle in school.
Vaguely. Combinations, right?
Exactly, combinations. They're crucial here because they dictate how different components of the polynomial, represented by the earlier S terms, combine together. They ensure all the terms are weighted correctly in each step of the recursion.
Okay, so they handle the combinations. What about the other parts?
Then you have the dash 0R pay R part. This involves the very first of the symbolic coefficients, A0R, which is related to the coefficient of the by 17 term in our example, raised to some power. This ties the calculation back to the initial setup of the polynomial in its new symbolic form.
Right.
And finally, the SUR1R term. This refers to earlier terms in the sequence of symbolic coefficients that we're calculating. This is the truly recursive part. Each new nest value, like SSD1R, is calculated using previously determined SUR values, the SR1 term.
Ah, I see. So you calculate the VOR, then use that to help calculate S1, then use those to get S2R and so on.
That's the essence of it. It systematically strips away layers of complexity by relating each new coefficient back to the ones already found. It's designed to reveal an underlying, perhaps much simpler structure within the polynomial that the classical methods, just looking at the surface coefficients, simply couldn't see.
That sounds incredibly intricate. Does this mean you have to calculate a huge number of these S coefficients for an 18th degree polynomial? Are we talking 18 steps, 18 coefficients?
You do. It's a rigorous systematic process. You calculate each skier R value step by step, following that recursive recipe. For our 18th degree polynomial, yes, you'd expect to potentially calculate up to S17R.
Okay.
But, and this is where the truly mind-bending insight comes in, this is where the aha moment really hits for this specific problem. What happens when you meticulously apply this recursive process to our specific 18th degree polynomial, the one with the coefficients -18, 153, -53, -816, and so on?
I'm on the edge of my seat. What happens? Does it simplify? Spill it.
What is absolutely astonishing and really highlights the power of this approach for certain problems is that for this specific polynomial, Ezouidi's recursive process reveals an incredible hidden symmetry.
Symmetry.
Yes, because nearly all of the derived symbolic coefficients, they just vanish. They calculate up to zero.
Wait, really? All of them?
Well, almost all of them. It's like finding a needle in a haystack. Only when you run the process, almost all the hay disappears, leaving just the needle. It indicates this polynomial, despite its surface complexity, had a surprisingly simple, almost designed internal structure that only this method could expose.
Wow. Okay, so which ones become zero?
To be precise, when you run the calculations starting from K0 for S1R, which relates to the constant term, and then K1 for 0 bar, K2 for S1R, and so on, all the way through K8, which gives you S7R, every single one of those evaluates to zero.
S0 through S7 are all zero.
Yes, and it gets better. After a crucial intermediate calculation related to K9, the process shows that the subsequent coefficients, S9R, S10R, all the way through 16R, they also turn out to be zero.
No way. So wait, let me get this straight. A whopping number of these coefficients, 0 through S7 are zero, and then S9 through S16 are also zero.
Yeah.
That's 8 plus 8. That's 16 coefficients out of the 18 possible ones simplifying to zero.
Exactly. It feels almost too convenient, doesn't it, for such a complicated looking equation?
It really does. Is that a common outcome when using Ezouidi's method, or is there something particularly special about this specific polynomial that makes it simplify so dramatically?
That is an excellent question, and it really highlights both the power and perhaps the specificity of Ezouidi's method, or at least its application in this documented case. This extreme degree of simplification, where so many of these crucial intermediate symbolic coefficients just collapse to zero, is indeed a profound revelation about this specific polynomial.
So it's not necessarily expected for every polynomial.
We can't assume that based solely on this example. What it means is that buried deep within the original monstrous equation, with all its large coefficients and terms, was an inherent structure, a hidden simplicity, a pattern that was completely obscured by its superficial complexity.
A pattern that classic methods just couldn't detect.
Precisely. Classical methods, looking at the polynomial term by term, coefficient by coefficient, would likely never uncover this underlying structure. It's like, imagine you have a highly complex, multi-layered drawing full of intricate lines, but then Ezouidi's method provides a special lens, and when you look through it, you realize the entire drawing is actually made up of just 2 or 3 simple repeating patterns that were cleverly overlaid.
That's an incredible analogy. So, okay, if almost all of these S coefficients become zero, which ones actually matter? Which ones survive this whole recursive process?
Only 2 key symbolic coefficients emerge from this process as non-zero and significant for determining the roots. We find SSD, which comes from the K9 calculation step. It evaluates to a specific non-zero symbolic value. The source gives it as mesion 48619 as 789.
Okay, SSD is important. What's the other one?
The other one is the final coefficient in the sequence, S17R. This emerges from the K18 calculation step, the very last one for this degree. And it also has a non-zero value, 488,662 by 1818.
So only SEDR and 17 are left standing. essentially.
Exactly. These two coefficients become the linchpins. They carry all the essential information needed to determine the polynomial's roots now that the structure has been simplified so dramatically.
So, this rigorous recursive calculation,
Mhm.
this is where the magic happens, as they say. By systematically determining these symbolic values, even though most turn out to be zero in this case, you're building a pathway to the exact roots, completely avoiding the imprecision that comes with numerical methods.
That's it. And in this particular, perhaps fortuitous case, that pathway becomes incredibly streamlined, almost shockingly simple.
Okay, so after all that complex step-by-step recursive calculation and the genuinely astonishing revelation that almost all the crucial is coefficients turned out to be zero, it boils down to something remarkably elegant. You said it's like finding a secret tunnel through a mountain. How does that simplification actually look in terms of our original polynomial equation? What does it become?
The transformation is, well, it's dramatic because Celer R through 16 are vanished, and then Sen R through 16 are also vanished. Our original 18th degree polynomial, which started as that long, intimidating string of 19 terms, from by 18 down to the constant, it gets shockingly simplified.
How
It
simple?
transforms from that initial lengthy form into a much, much simpler expression. The polynomial px equals 0, 0 becomes equivalent to by 18 arrow by 9 plus S17R equals 0, 0.
Oh, that's it.
That's it.
From 19 terms
Yeah,
down to just three significant terms,
Yeah.
x to the 18th, x to the 9th, and a constant.
exactly. Everything else effectively canceled out through the recursive definition of those things coefficients.
That is truly astonishing. An 18th degree equation, which looked like chaos, boils down to something that, well, it almost looks like a quadratic, doesn't it?
Mhm.
How does an 18th degree polynomial suddenly behave like a quadratic? It's genuinely mind bending.
It is, isn't it? And that raises that important question again about the hidden structure this method reveals. The real ingenuity here, the next step in the process, is recognizing that this simplified three-term polynomial can be viewed as a quadratic equation, just in disguise.
In disguise, how?
Instead of x being the variable in the quadratic equation, the variable is actually by 9. Think about it. By 18 is just by 9 too.
Ah, okay, I see it now. By 9 squared minus some number times by 9 plus another number equals 0.
Precisely. Our simplified polynomial by 18 multiplied by 9 plus S17R equals 0 becomes by 9 2 plus S17R equals 0. It's a perfect quadratic form, but the variable being solved for initially is by 9, not x.
That is brilliant. It's a testament then to the power of Ezouidi's symbolic transformation, how these seemingly unrelated high-power terms can elegantly collapse into a form we all know how to solve.
Exactly. A quadratic form is universally solvable.
So if we're essentially dealing with a quadratic equation now, but where the variable is actually by 9, that means we can use the good old quadratic formula, right? The one most of us probably learned in high school. Minus b plus or minus the square root of b squared minus 4k, all divided by 2a.
That exact formula. We apply it directly, but we apply it to find the value of by 9.
Okay.
So using the formula, by 9 equals S8R Breganese Sport SAR 241 S17R 21.
Where CR and S17R are those specific symbolic values we found earlier.
Correct. The term inside the square root, S8R 24 S17R, is the discriminant. The source calculates this discriminant value and calls it Nenikes1R8, giving it the value Nesh 363612673 by 1818.
Whoa! Okay, still dealing with large numbers, but they're exact symbolic numbers.
Yes, the arithmetic is still complex because the values of CIR and S17R involve powers of 18, but crucially, it's now a straightforward path using a known formula to an exact solution for by 9.
So we plug in the values for 8R, which was Maxish 4816 RAX 189, and S17R, which was 48622881818, and the calculated discriminant. And we get the value for by 9. But that's by 9, not x. How do we get the actual roots x?
Right. Once you have the two possible exact symbolic values for by 9 from the quadratic formula, one with the plus sign, one for the minus sign, you then need to take the 9th root of each of those values.
Ah, the 9th root. And taking a 9th root gives 9 different answers in the complex plane, right?
Exactly. For each of the two values obtained for by 9, taking the 9th root yields 9 distinct complex roots. Since there were two values for by 9, this gives us a total of 2 times 9, which is 18 roots.
Which is exactly the number of roots we expect for an 18th degree polynomial. It all fits.
It all fits perfectly. The fundamental theorem of algebra is satisfied.
So can you give us the final form of that exact root? How does it look after all these substitutions and taking the 9th root?
Indeed. After all the calculations, the exact roots for the polynomial, all 18 of them, are expressed beautifully and precisely using complex exponentials, which handle the multiple roots from taking the 9th root. The source provides the form for each of the roots as xk equals 18 plus 18, Cashbart 2363612xe73, 219, xq2 pi ik9 for k equals 0, 1, 2, up to 8. Note, the original outline had a slightly different representation involving 2p Terra, which might be a simplification or alternative notation, but using the standard complex exponential form xp2por for nth roots is more common and clear.
Wow. And there it is. Okay, that formula still looks complex, but the key is it's not an approximation. It's not a close enough. It is the exact precise answer expressed symbolically using integers, roots, and complex exponential.
That's the payoff.
It's truly astonishing how this theorem, through that recursive process and simplification, provides that level of absolute certainty for such a complex initial problem.
It really is.
And just to clarify again for listeners who might not be immediately familiar, you mentioned complex